All right, let's pull back the curtain on something that honestly powers pretty much every piece of software you use. I'm talking your phone, the global financial system, you name it. We're talking about data structures. They're the invisible architecture that makes everything work. Let's dive in.
It all starts with this really simple but powerful truth. We love talking about flashy algorithms, right? The secret sauce of software. But we forget something so basic. Before you can do anything, your data has to live somewhere. And that is what data structures are all about.
And here's why that is so important. How you choose to store your data, well, it's not a small detail. It's a decision that has huge consequences. It literally determines what's going to be fast, what's going to be slow, and in some cases, what's even possible to build in the first place. So, just a quick heads up on what we're doing here today. We're not going to be writing a single line of code. We're not getting lost in the weeds of implementation. I want you to think of this as a map, not a manual. The goal here is to give you the lay of the land so you can build these really clear mental models of how all these pieces fit together.
So here's our game plan. We'll start with what a data structure even is. Then we'll explore the 5 main families, look at some key examples, and then, crucially, talk about how to pick the right one for the job. And we'll wrap up with the core truth of it all.
All right, section 1. Let's tackle the big question. What is a data structure really? Because I promise you, it is so much more than just a box you stuff data into. Here's the key idea. It's a disciplined way of organizing things. Think about it like organizing your closet. Sure, you could just throw everything in a giant pile on the floor. But finding a specific shirt, good luck. That would be a nightmare. A data structure is like a perfectly organized closet where everything has its proper place. It makes finding exactly what you need, right when you need it, super easy and efficient. Now this is where it gets really fun. See, there's no magic bullet. There's no single best data structure that solves every problem. It is all, and I mean all, about trade-offs. Each one is basically an answer to these questions you see here. And each one makes some things incredibly cheap and fast while making other things really hard and slow. That's the game. So to make sense of this world, we can group all these data structures into 5 main families based on what they're trying to do, their intent. This is how we're going to organize our map. First up, we have sequential structures, where the order is absolutely everything. Then there's constrained access, where strict rules tell you how you can get to your data. After that, associative structures, where finding something by its unique identity is priority number 1. Then hierarchical, for modeling things like parent-child relationships. And finally, we've got network structures, which are all about modeling complex, free-form connections. Okay, let's dive into our first 2 families. Now, these are probably the ones you're most familiar with. They're all about order and rules. And here we have the classic trade-off. An array is like a numbered parking garage. You know exactly where spot 101 is, right? Access is instant. But trying to add a new spot in the middle, a total nightmare. A linked list, on the other hand, is more like a train. Each car just knows which car comes next. It's super easy to insert a new car anywhere in the train. But to get to the 101th car, you gotta walk through the first 100. It's a simple choice: fast access or a flexible structure. Next up are the constrained ones. A stack is just like a stack of plates. You can only add a plate to the top or take one from the top. The last one you put on is the first one you take off. This is literally how your computer's undo function works. Then you have a queue, which is like a line at a coffee shop. First person in line is the first one to get coffee. This is essential for stuff like print jobs or network requests, to ensure fairness and order. And here's the real insight. This reveals a pretty deep truth. The very flow of a computer program, how it decides what to do next, is often a data structure problem in disguise. And yep, stacks and queues are the unsung heroes of that story. Okay, moving on. Let's look at structures that handle more complex situations, where it's not just about what comes next, but about who's who and who is related to whom. So let's talk about the hash table. This is the undisputed champion of fast lookups. If you need to find a student's record by their ID number or a product by its unique code, this is your go-to tool. It's like a magical dictionary where you can jump to any definition instantly without having to flip through all the pages. The most important thing here is identity, not order. So what's the catch? Well, here it is, and it's a big one. Hash tables are crazy fast because they completely throw away the idea of order. You can find anything in a blink, but don't even think about asking what's the next item, because in the world of a hash table, that question makes no sense.
They trade all that structure for pure speed. Now for hierarchies. A tree is just like a family tree or the file system on your computer. Everything has a parent, and things are kept in a nice, sorted, structured order, which makes searching really efficient. A heap, well, a heap is different. It's still a hierarchy, but it only cares about one thing: priority. It's built to always give you the most important item, the highest or lowest value, instantly. Think of an emergency room triage system. They don't care who arrived first, they care who is the most critical. That's a heap.
All right, on to our last family of data structures, the most flexible of them all. And right after that, we'll talk about how you can actually use this map we've been building to make smarter design choices.
A graph is the ultimate way to model complex connections. Just think of a social network, right? People are the nodes, and their friendships are the edges. There's no top, no bottom, no single parent, just this web of relationships. This is the structure that's working behind the scenes when Google Maps finds you a route or LinkedIn shows you your connections. It's just pure, unconstrained relationships. Okay, so we have our map. We know the lay of the land. But now for the million-dollar question. When you're actually sitting down to build something, how do you choose the right path?
The secret is just asking the right questions. What are you going to be doing most of the time? Is it searching, adding new things, deleting old stuff? Does the order of things matter at all, or is it all about finding things by a unique ID? If you answer these questions, the ones you see right here, they will lead you straight to the right data structure for your problem. You have to remember, data structures are answers to questions. They're not just default choices you make.
And that brings us to our final and I think most important idea in this whole explainer. It's time to zoom all the way back out and really see the big picture.
This is it. This is the core truth. Algorithms, they get all the glory for making things fast. But it's data structures that actually define the realm of what is possible. The right structure doesn't just make something a little bit faster, it can make the impossible possible.
So here's my challenge to you. Don't just memorize the names of these things. Try to really deeply understand their purpose, their strengths, and their weaknesses. Because if you can do that, you'll find that all those clever algorithms and elegant solutions, they'll just start to follow naturally. Thanks for coming on this tour with me.